is asking what is an extraneous solution. The key word there, an extraneous, a root word there is extra, right? Okay, so that's kind of what we're referring to here. But mathematically, it's a solution to our original equation that doesn't actually satisfy the equation. So we're going through some algebra, and it generates these solutions, but an extraneous solution is one of those that does not, when you plug it back in, it does not provide you a true statement. It does not satisfy the equation, okay? And that's something to think about. That's terminology I'm going to use. Does it satisfy the equation? And when I say does it satisfy, hopefully you link that word to does it give me a true statement in the original equation? Okay? Does it give me left-hand side equal to right-hand side? I'm going to plug it back in. Extraneous solutions show up because of the algebra that we're doing. Okay? Because we might have an equation that looks difficult, or we maybe don't have techniques to address it. So we start going through our algebra. Maybe we go through a squaring process. Maybe we go through a process that deals with like a common denominator or something like that. Okay? And that process starts to change our equation to something that we can manipulate. All right? And we go through and solve that equation. And all the solutions that exist to the first equation will exist in the subsequent equations that we create through our algebra. Does that make sense? We've shown that with graphs, right? However, not all of the solutions of our final result are true solutions to what we started with. Okay? So all your solutions to the original equation are in your final work, but there might have been some extras created. Okay? And we got to be able to sift those out. Kind of two things that we're going to talk about in a lot of details when we take the nth root of something. So we take square roots, fourth roots, sixth roots. Okay, when the root is even, to get rid essentially of that root, we're going to square things multiple times. Okay, if it's just square root, well, obviously we'll square it, get rid of square root. If it's a fourth root, we actually square twice. It could be raising something essentially to the fourth power, right? If it's the sixth root, I would square it 3 times. So that's going to be something essentially the sixth power. So when we do that, that's a situation where a lot of extraneous solutions develop with that algebra. And when we start talking about logarithms and that kind of stuff later on, more extraneous solutions show up there. Is that all right? Okay. Now, when you're doing these, my suggestion to you right now is that when you look at them, you're not going to know. Example 1 has no extraneous solutions. Okay. Example 2, by the format of it, has 1 extraneous solution. You're not going to know that. So you need to probably consistently take your answers and plug them back in. I'm going to show you some short techniques of doing that with varying different types of technology that you might have. Okay? And with those technologies, there's even maybe 2 or 3 different ways to do it within those. Okay? So I'll show you a couple of those things that you can use to check. Ultimately, you don't need the technology. You can do it by hand if you want to check by hand, but sometimes that just gets problematic. Okay? All right, so example 1 there says 5 equals the root of 4x minus. And actually, I don't want to do that one first. I want to actually go back. I want to go through the same kind of structure that I worked with the last class. So let's actually jump down to a different style of question. We'll come back and do those by the end of the period. I want to do these first. Solve an equation with rational exponents. And the reason I want to do this is because I think some of the things that the procedures that are involved in here might be fresher in our minds right now because of what we did last week. I think it makes sense to do these first. All right, so we got rational equations. Or sorry, not rational. We got equations with rational exponents. Okay. That looks daunting. It looks challenging. It looks ugly. Okay. And sometimes, guys, and you have to fight this. Okay. But when you see an equation that is challenging or daunting or whatever. Okay, maybe you're the kicker for the Browns and he shows up tomorrow and he's got to kick again tomorrow. It's going to look challenging to him, right? It's going to be a daunting task, okay? When you've not maybe had the success that you are used to and you start seeing these equations that look more difficult, your desire, your instinct is to shut down sometimes, right? And just to skip it, don't do it, okay? But fight through it, okay? Work through things, okay? Do internet searches, do Google searches, go to YouTube and just type in equations with rational exponents, And I guarantee you, somewhere, it's not going to be the exact same equation, but you'll be able to find something that kind of leads you through the process, right? Kind of holds your hand maybe with another example, something like that, that you could then address this with. But when we do this one, you're going to look at your exponents, and here we've got some negative exponents, right? We never want to deal with negative exponents, okay? They're kind of a pain in the butt. So we're going to rewrite this so that all of our exponents are positive. So that means, okay, so we got x to the 3/2, that stays that way. X to the 1/2, that's positive. Now how do I write this last term so that my exponent's positive? First of all, here's the question. What does my exponent go to? Does my exponent go to the 25? Does it go to the x, or does it go to both? It goes to the x. Remember, the exponent is applied to the object that it is directly behind. So it's directly behind the x, right? Okay. Now, if it was parentheses like that, then it's directly behind the 25x, right? Does that make sense to everybody? Okay. So we got to pay attention to that notation, but right now it's just to the x. So the 25 is going to stay 25, right? Now, what do I do with the x to the negative 1/2 to make it a positive exponent? Yeah, you're putting it down there, right? You guys remember doing that last year? Okay. Should have even done a little bit of that in Algebra 1. Okay. Your laws of exponents were in Algebra 1 standard. Okay. So I look at that, and now we have an equation. I should have put equals 0 over there, but we have an equation that has some denominators, right? And when we have an equation with some denominators, we like to get rid of those denominators as fast as possible, right? So what am I going to try to multiply everything by here? Just give me the word or the concept that's going to allow us to work through this. I want to get rid of denominators. What do I need to multiply everything by? Not reciprocals. If I had, let's say I had just the equation 1/2 x plus 2/3 equals 1/4. What would you go through and multiply everything by there? Least common denominator. Okay, so that's what we're looking at. Now the least common denominator is going to be a variable term. That's fine. Okay, it doesn't have to be solely numerical. Okay, so when I go through here, I got a denominator of 1, denominator of 1, so obviously that's incorporated. But then I have a denominator of x to the 1/2, right? So there's my LCD. 1 times 1 times x to the 1/2. Okay? So I'm going to go through and multiply every one of these terms by that LCD. So my hopes are that you guys remember when we started working with some of the equations last week, and I think we did even when we worked with the linear equations, we've talked about the LCD process, right? Multiplying by least common denominator to every single one of these terms. So multiply that by x to the 1/2. Multiply that time by x to the 1/2, multiply that by x to the 1/2. And something that people forget is that you're actually multiplying that one by it as well, but it's kind of trivial. It's going to give me 0, right? Okay. But if I go through here, what do I do if I have x to the a, and in this case, maybe my a is the 1/2, and then I have x to the b, and maybe in this case, my b is the 3/2 in that first term. How do I do that? What does that turn into when I multiply like bases? What do I do with those exponents? Add them together, right? So that's the rule that we talked about in regards to maybe Algebra 1, Algebra 2 law of exponents. You're going to add the exponents when you're multiplying like bases. So that's what we're going to go and do through here, okay? Obviously, nothing cancels here, so I'm going to multiply those. X to the 1/2 times x to the 3/2 gives me x to the, say again? Careful. You already got common denominators, right? So it's going to be 4/2, isn't it? I add those to 1/2 and 3/2, gives me 4/2. So it gives me x to the 4/2, which is just x squared. What's going to happen here? X to the 1/2 times x to the 1/2. X to the first, right? Make sure we're not, I see what we're doing here. Because I heard 3/4 on the first one and I heard 1/4, right? What are you doing there? You're doing power to a power, right? Remember, power to a power is going to look something like this, where it's x to the a raised to the b. Now that would be xab. But when we're multiplying like bases like that, then you add the exponents. Okay? And then that last one, what's going to happen with the x to the 1/2 up top? Yeah, it cancels that 1 on the bottom. So that just leaves me plus 25. Gives me 0. All right? So initially, the equation we started with had rational exponents. It was not quadratic. I'll show you the picture of it when we're done. But it's nowhere near being quadratic. Okay? But we go through a little bit of analytical algebra. We know we're allowed to do. We know we're allowed to multiply both sides of the equation by the same thing, as long as we do it correctly. And now it generates this equation. And that's something we can mess with, right? We know how to manipulate that. So that's going to factor to x minus 5, x minus 5. And in both situations, x is equal to 5. Okay? When you're done, okay, because we multiplied by that x to the 1/2, okay? Essentially we multiplied everything by square root of x, didn't we? Okay. We're probably going to want to make sure that we check to see if there's any extraneous solutions. Anything up there that doesn't really make sense to us. In 5, since it's only our answer, that's what we want to check it once, right? I want to kind of go walk through the process here, maybe graphically at first. Alright, so let me get a new window here. Alright, so what we started with was x to the 3/2. Alright, so x to the 3/2 minus 10x to the 1/2. Make sure that when you're doing this, you put your, see how I'm putting my exponents in parentheses? If I don't, it's going to take, if I just leave these parentheses, these green parentheses off down here, it'll take 10x to the first, and it'll multiply it by 2, so it'll give me actually 20x there, okay? So make sure that we, it'll divide by 2, so, sorry, that'll give me 5x. So make sure you put it in parentheses. But then we go plus 25x to the negative 1/2. I graph that thing, and we're looking at it. Okay, now you might say it looks something parabolic, but it's kind of skewed to the side, isn't it? It's kind of pulled out that way. So that graph is not parabolic. Okay? But the solution there, we see that we're getting 5, right? What we did algebraically by hand is we actually generated what I'm going to show you in this yellow graph, which we said was x squared minus 10x plus 25. We're interested where that equals 0, and we do know that equals 0 at 5. And that is parabolic, right? Okay. Now this is kind of a unique situation where the one solution here gives me the one solution there, and it's because it was tangent here. But those two graphs are different, right? Because the algebra that produced them was different. But what I want you to know, and what you need you to know, is that all of the solutions of the green graph exist as solutions in the yellow graph. Okay? And now that phrasing leaves it open to say that there could be more solutions in the yellow. Okay? So the yellow one might have 2, 3, 4 solutions. But within those 2, 3, 4 solutions will be your one that comes from the green graph, or that is in the green graph. Does that make sense? Okay? And the ones that aren't, those are your extraneous ones. All right, we'll see through a couple examples later here, maybe a more obvious thing happening over here where we get one solution, but over here maybe we get 2 or 3. Okay? Using your TI-83 or 84, guys, to check for extraneous solutions. Because obviously you can check them using your graph, like I did. So let's see here. So let's say we do all the work by hand, and I graph that then, and I say, oh, yep, 5 was the only answer, so that eliminates any extraneous solutions, right? Okay, or I'm able to decipher which ones may or may not be extraneous. Using my TIA 3 or 4, we can do the same process using substitution, okay? Because ultimately what we need to do to check extraneous solutions is this. We need to go in to our original equation and say, okay, if x is 5, I'm going to rewrite this. You guys agree that that would be x cubed, and then you take the square root of that? Okay, because that's a root 2, right? Okay. Minus then 10 times the square root of x, plus then 25 over the square root of x. Is everybody okay with me writing it that way? That's exactly what that means using the root symbol. Well, if I now know x is 5, can I come and say, well, it's the square root of 5 cubed, which would be 125, minus 10 times root 5, plus 25 over root 5. Is everybody okay with that? Let's do a little bit of simplification here. Let's say that, is this 25 times 5? So can I rewrite that as 5 root 5? Is that what that simplifies to? Minus 10 root 5. Now can I rationalize this one? Okay, so if I go 25 over root 5, rationalize it, gives me 25 root 5 over 5, right? What's going to happen with that 25 and that 5? They cancel, right? Give me 5 root 5. So this thing here simplifies to that. What does that give me? Plus 5 root 5 plus 5 root 5 minus 10 root 5. 0. So I got a 0 on the left hand side. I got a 0 on the right hand side. That's an absolute true statement, right? Tells me x mean 5 is the right answer. Okay? Now, I think that's good that we can do that, and that you do that, okay? Because it's going to increase your skills in root work, it's going to increase your skills in order of operations, all that kind of stuff, evaluating. However, if you're pressed for time, maybe this is an option. I'm going to go to y equals. I'm going to type in my equation in y1. Okay? Only thing here you got to be careful with is that you put your exponents again in parentheses. Okay? And you could have also written it like this, using the root symbol if you want to. I just think that's a little bit harder to type in. But now I'm going to say it quick, because I'm not going to use the graph. I'll show you multiple techniques you guys can use with this calculator. And what this one's going to do essentially is what we did by hand. We went back and we plugged that 5 in, right? So I want my calculator to evaluate this equation on the left-hand side at 5. So the way we're going to do is we typed in a y1. So I'm going to recall y1. I'm going to go hit my vars button, or variables button. Okay? I'm going to go over to y vars. And it gives me the types of different types of equations that I could have typed into y1. You type in functions, you type in parametric equations, you type in polar equations. We dealt with functions. Okay? If I'm using x as my input, I'm dealing with a function right now. So I'm going to hit function. It's going to take me to y1, y2, y3. And we used it y1, right? So I'm going to take y1, I'm going to hit enter on y1. And basically right there, when I do that process, guys, I now have written in there x to the 3 halves minus 10x to the 1 half plus 25x to the negative 1 half. Does that make sense? I'm going to open up a parenthesis. What happened? Alright, so I had y1 in there. I open up the parenthesis. I'm going to put my 5 in because that was what I want to evaluate it at. And then hit enter. And it does all that algebra for me, right? Okay, now I see the left-hand side was 0, the right-hand side was 0. 5 is my answer. It worked. Is that okay? Something to be cautious of, just because you only have one solution, I would not make the judgment or the conclusion that it is a true solution. Okay? Always check it when you're dealing with square roots. So, let's do one more of these. All right, so we'll do example 2 up there. Very similar to the last one, but it adds a little tweak to it. You'll rewrite this as x to the 1/2. Minus now 1 over x to the 1/2. Notice that's a negative exponent there. Minus then 6 over x to the 3/2 equals 0. And the tweak that occurs here, the reason this one's a little bit different than the last one is now we have 2 denominators, right? So we now have to go through that process of choosing an LCD. And remember, when we choose an LCD, we need to go through and choose every single factor that is new. And if there are any bases that are the same, you choose the one that has the higher exponent, right? Okay? Well, when I go through, and I'm just going to rewrite this just to kind of prove the point even a little bit further. Would you guys agree that x to the 1/2 can be rewritten that way? Now, my argument, you might not say, well, why are you doing that? It doesn't really do anything. But it's in comparison to x to the 3/2. Would you guys agree that x to the 3/2 can be rewritten that way? And the reason I rewrite that is because I want you guys to see that when I have x to the 1/2 and x to the 3/2, those are not different bases. Okay? They can be rewritten or reorganized so that they are the same base. So I don't need to choose in my LCD x to the 1/2 and x to the 3/2. Does that make sense? Because if I did that, then my LCD is going to be what? X to the 3/4. And then things are going to get messy, and things aren't going to, we're not going to get rid of these rational exponents using x to the 3/4. If I do this, now I can see, well, those are the same bases, so I choose the one with the higher exponent, right? So I choose x to the 1/2 cubed. That is now my LCD, which is essentially just x to the 3/2, right? So I'm going to go through and multiply every single one of these by x to the 3/2. And there's going to be some nice kind of cancellation occurring here and simplification that occurs here that would not occur if I would just use some arbitrary common denominator. Okay? Is that all right with everyone? So even if I did use just x to the 3/4, at some point the process that we just went through, the process that we're going to go through, still has to be conducted at some point. Okay? So it just makes sense to do that as soon as you can. Now when I take in every one of those terms and multiply by x to the 3/2, what am I going to get when I multiply right here? X to the 1/2 times x to the 3/2 gives me what? X squared again. Okay? Right here, okay? Now if you remember, if I have x to the 3/2 over x to the 1/2, that rule, if you remember back to algebra, if I had x to the a over x to the b, you guys remember what you do with the a and the b? You subtract them, so it's a minus b. So multiplying like bases, you add the exponents. Dividing like bases, you subtract them from numerator minus denominator. So it's going to give me just minus x, right? X to the first. And now what's going to happen with this x to the 3/2 and this x to the 3/2? Yeah, they're going to cancel each other out. So it gives me minus 6 is equal to 0. It transformed it into a quadratic, right? We can solve that quadratic. And a lot of times when we do these, you know, obviously that algebra is something we can do real quick. We're going to get x minus 3, x plus 2. So x is equal to 3, and x is equal to -2, right? Alright, so if I go to y1, type that in, x to the 1/2 minus x to the negative 1/2 minus 6x to the negative 3/2. I just used decimals, I just thought it was a little bit easier to type in maybe. I'm going to go second quit. I'm going to try to evaluate this. And now it's real nice because I've already done a problem like this. I've already used y1. So it's going to recall it. Now it's using the y1 that I just typed in, so it's using this one. I'm going to type in 3. See what I get. I get 0. What does that tell me about 3? True solution. Okay? I'm going to try -2. So I hit second enter. Plug in -2. Non-real answer. Okay? Meaning that when I do that, and just think about this. Look at that second term, the 1 over x to the 1/2, right? When I plug in -2, then don't I take square root of -2? Well, can you take square root of a negative number? No, it gives you imaginary, right? Which imaginaries are not part of your real, so that's why it's a non-real solution. So -2 is not a solution to this. Okay? It does not satisfy the initial equation. Okay? If you were to graph it, my window's not all that great, but that is -3 right there. This would be -2, sorry, +3. This is -2 right here. You see, we do not cross that -2, right? And that's what this work is telling you. This work is telling you do cross there. But we only cross at -2 for that. Okay? So that's what I want to show you here real quick. The original problem, x to the 1/2 minus x to the negative 1/2. Was it -6 then? X to the negative 3/2. Okay. So that's what I'm looking at right there in the first equation, the original equation that we worked with. And it's equals 0, so we're looking where does this thing cross at 0? And obviously you're seeing here it does it at 3, right? Okay. Now if I do what we did by algebra by hand, we had x squared minus, is it x minus 6? And we're looking at where that thing crosses at 0. So you're seeing that the graphs are two completely different things, right? But all of the solutions to this yellow one reside in the solutions of the green graph, right? Okay? So the green graph has solutions at -2 and +3, and one of those is the solution to the original equation. Okay? Does everybody understand that idea of what's going on in the background when we're doing this? Okay? And that's critical. It's going to make the process that we go through a lot easier later on if we can understand that that aspect of things. All right, so let's come back up then to these root equations. That third example that I had with those rational exponents can be addressed using the concepts that we learned here. I think a little bit easier using the concepts we learned here. All right, so this gives me we call these root equations or radical equations. You've done them before, but I want to talk about them because there's some key, very, very important steps that people neglect. They forget about them, and that key thing is the fact that a lot of times when I see A plus B, A plus B, and I square it, that is not just A squared plus B squared, correct? That's the number one error that people make all the time when they're dealing with root equations. is that they say, and when I square a binomial, it's just the first term squared plus the second term squared. You're missing the O and the I there, right? Okay, so you gotta pay attention to that. That's not an issue on this first one, but it will be pretty soon. So when we deal with root equations, okay, that's a huge error. Another huge error is that people forget to isolate the root part before we start applying the inverse operations. Okay, if I have a square root, the inverse operation is power of 2, right? If I have a cube root, the inverse operation is a power of 3, and so forth. Okay, but I can only use those in a meaningful or beneficial way if the root is isolated. Okay, and I'll give you an example. I think example 2 we'll go through it where we don't isolate it, and it should prove to you the purpose of getting this by itself. So it's already by itself here. So we're going to go ahead and square both sides, right? Square both sides, you get 25 here. And when I take a radical times itself, I'm just left with the radicand, right? So radical 3 times radical 3 gives me 3. Radical 7 times radical 7 just gives me 7. Radical x times radical x just gives me x, right? So radical 4x minus 3 times radical 4x minus 3 should leave me with just 4x minus 3. Add 3 to both sides. Divide both sides by 4. 7 is equal to x, right? We should check that. We should plug that back in. I get 4 times 7 is 28, minus 3 is 25, right? What's the square root of 25? 5. So you get the left-hand side equal to the right-hand side, right? We know that's a true statement then, okay? The argument here, guys, is that if I were to look at this thing as a graph, okay, so the line y equals 5 might be there. The root 4x minus 3, so it's going to be, just give me a second real quick, 3/4. So it's going to, if 1 is there, it's probably going to start like right there. And they're going to cross, and at that point right there that they cross would be 7. That would be the x value of that point. What we look at here, now it's 2 lines. It's the line y equals 25 and line 4x minus 3, maybe that, okay, where that's negative 3. They still cross at 7, right? So looking at a radical curve and a root curve and a line, the intersection is the same thing once we transform it to the intersection of those 2 lines. Okay. Let's do a harder one. Again, nothing you haven't seen before. Okay, but 2x equals 1 minus root 2 minus x. And I want to approach this first kind of the incorrect way. Because this is what a lot of people want to do. They see that square root right away and say, oh, I got to square things. I have to square things. So I'm going to do this on the board over here. And they see that they have 2x is equal to 1 minus root 2 minus x. Now, in order to see that squaring right away is not going to be beneficial here, we have to understand this first rule that I wrote up here. That's not true. Because a lot of people that square right away also think that this is true. Okay, the fact that these should be equal. All right. But I want to show you why it's necessary to isolate. Because when we square things, we're trying to make things look simpler, right? Trying to get rid of the roots. Well, if I do this correctly, if I just square the left-hand side, and then just square the right-hand side. Left-hand side gives me 4x squared, right? Right-hand side. How many terms do you have there? You have 2, right? Okay, or 2 objects. You have the 1 and then the root, right? So you got a binomial. And if I want to square that binomial, it should look something like this. Correct? Okay. FOIL that. First times first is 1. Okay. Outside times outside gives me negative root 2 minus x. Inside times inside gives me another negative root 2 minus x. So I get minus 2 root 2 minus x's. And then last times last should give me, what's a radical times a radical? Just a radicand, right? So it just gives me 2 minus x. What was the purpose of using inverse operation? What's the purpose of squaring? To get rid of what? Get rid of the radical, right? Did we do that? No. Okay. As long as if we follow all our rules right, that did not get rid of that radical. Okay. Some people And I think this is a great kind of place to put this in. Some people struggle foiling something like that because it's kind of ugly, right? Well, can I say, let's let u equal root 2 minus x? Do that. Can you foil that pretty easily? Yeah, you're going to write 1, and then it turns into minus 2u plus u squared. Well, that's 1 minus 2u was root 2 minus x. U squared, well, if I take u squared, square that just gives me 2 minus x, right? There's a plus sign there. So you can use that u substitution there as well to maybe simplify some of your steps of algebra if it gets kind of messy in regards to foiling or something like that. But that is why we need to isolate the radical first. We need to get that thing by itself. I'm a person, I like to deal with my radical being, I like that to be a plus sign. Okay, so I'm just going to rewrite this as root 2 minus x. So this would be what? 1 minus 2x on the right hand side. Is that okay? All right, guys. So if we were to look at that graphically, at the onset, what we have is some line 2x intersecting some curve, some radical curve. Okay, and they're going to intersect one time, I believe, in this example. But as we go through the work, we get extra things to show up. And now I can square. When I square the left-hand side, I get 2 minus x, right? Radical times itself is just that radicand. Now on the right-hand side, how many terms do you have there? You have 2, right? You're squaring a binomial, so what do you have to do? You have to FOIL. The number one place that people make a mistake here is they write 1 plus 4x squared. Okay? And those are parts of things. I mean, that's part of the whole thing, 1 and 4x squared. That's first times first, and that's last times last, but you need your O and I, right? My O and I are going to give me another negative 4x. What did we just turn this root equation into? Quadratic equation, okay? I'm going to get this equal to 0, so I'll move my 2 over, move my x over, so it's going to be 0 here, 4x squared minus 3x minus 1, right? And this is the reason why we spent time working with quadratics, because now we should have a hierarchy of factoring techniques we can go through, okay? I can't make the a 1 here, right? Can't divide everything by 4, so that's out the window. There is no GCF, and that's kind of looking at the a, trying to make it 1. The next thing is AC method, right? Or the quadratic formula, whichever you prefer. I think the AC method here is a little bit quicker. If I take 4 times negative 1, it gives me negative 4, right? Or 2 factors that give me negative 4, but add up to give me negative 3. Negative 4 and 1. So now I'm going to rewrite this as 4x squared minus 4x plus 1x minus 1. Okay, remember that's just rewriting that b term as the sum of those two things. Can I group now? Group those two. Group those two. What can come out of the first two? 4x. Leaves me with x minus 1, right? Now that x minus 1 is already what we need, right? Okay? So what can come out of these to keep it as x minus 1? So it's going to be 4x plus 1 as a factor, and x minus 1 as a factor, right? So my two solutions then are x equals positive 1, and x equals negative 1/4, right? Okay. Now, I'm just going to show you real quick. I know it might be beating a dead horse, but we need to see. We need to see what's going on graphically. All right. So in the yellow, I'm going to do what we started with: 2x, and then the other side was 1 minus square root of 2 minus x, right? All right, so in the yellow gives us that. And you see that that's probably an x value of negative 1/4, right? Okay. It does, those two things do not intersect anymore. This is a line This is a smooth curve, and it's going to keep getting lower and lower, but they never come back and meet again. Okay? So one solution there, right? When we went by hand and did the work by hand, we ended up with the equation 4x squared minus 3x minus 1, and we asked where does that equal 0? Now you're seeing that occurring at two spots, right? Negative 1/4 and positive 1. So the solutions to this exist in the solutions to this, right? But are we seeing an extra one? Are we seeing that 1? The solution we did by hand does not satisfy this thing up here. Okay? And the reason for that, guys, plug in 1. If I plug in 1 right there, I get 2, right? If I plug in 1 right here, what do I get? What's 2 minus 1? 1. What's root 1? 1. What's 1 minus 1? 0. Does 2 equal 0? No, it's a false statement. Okay, so it cannot be a solution. It does not satisfy the original equation. Now, here's the thing. Anything of that form might provide one solution, might provide no solution, might provide one or two solutions. Because look at this. So this is, I guess the argument I'm trying to make, guys, is if I start off with that, and people say, okay, well you had a linear component on the left, you had a root component on the right, I end up with one solution, right? So I say, okay, the next one, when I see if they 0.3x equals 1 minus root 2 minus x, I only have one solution. But if I change this, if I change the slope of that to 0.3, do you see that there, in that original equation, you should have two solutions? So when I go through the work algebraically, those two solutions that I get would both work. Does that make sense? Okay. So that's the argument that when I look at a problem, I may not know by looking at the algebraic representation of a problem, I might not know how many solutions are going to be extraneous or how many are going to be true, just based off of what I've seen in the past. I have to go through the manipulation of the numbers, do the plugging in and all that kind of stuff. Eventually, maybe we can talk about some domain ideas that might eliminate some things. But again, it's always going to be beneficial to plug things back in to see if you get true statements. Is that all right? Okay, so the web assignment assignment 1-6, it's opened up. You can go back in. If you've already worked on that handout, the numbers should coincide. Make sure they do before you start typing in. If they don't coincide, hopefully I forced it that way. I know I tried to. I don't know whether it's stuck or not. Be another thing we have to figure out. But if it's not coinciding, come talk to me so that I can send out information to everybody. If they don't coincide, I'll probably just extend the assignment a couple days. I know it's extra work, apologize, but it's just the way kind of things unfolded with web assignment not working for a while. So that's going to be due right now, tentatively Thursday. Okay. Hopefully tomorrow we can get through some absolute value stuff. And we talk about absolute value inequalities, absolute value equations, all that kind of stuff. And that can be 1, 2, maybe 3 days of that stuff in itself, depending on how far we get into it right now. All right? Fabulous. You're welcome for Friday.
Hmm?